Hello, class. Welcome to today's lesson. I want to take a moment before we start our work in graphing trig functions and just talk about on-course for a minute because I want to make sure that you understand what the grades indicate in the gradebook. So for any of the assignments that are graded based on completion and effort, those are like daily assignments. It'll say that in the name of the assignment. For something that's graded based on accuracy, like the assessment you did yesterday, it'll just have the assessment title instead. So for the things that are graded based on completion and effort, if you see full credit, like 3 out of 3, 2 out of 2, 4 out of 4, something like that, you're good to go. You've been marked present. I got your work. If you have something that's graded based on completion and effort, and you see a 0 out of 2 or 0 out of 3 or 0 out of 4, what that indicates is I did not receive that assignment from you, and I will have emailed you or sent you a message through a Google assignment. So if you ever see a 0 on something, it means I did not receive it. You should go check your email and follow up so we can get you marked present for the day and get you credit for that assignment. Third possibility when something is graded based on completion or effort is that you have something that's incomplete, like a 2 out of 4 or 1 out of 3, something like that. What that type of score would indicate is that the work you submitted didn't quite demonstrate to me that you understood all the content. So what that means is I will have emailed you or I would have sent you a message through a Google assignment and asked you to do something else, either send me some more of the work or make a couple corrections and resubmit it. And once again, you won't have an incomplete on something that's graded based on completion and effort without me contacting you. So go check those emails and you'll find out what I wanted you to do to follow up. Last possibility in the grade book is that something says no grade. All that indicates is I haven't had a chance to either grade the assignment or update on course yet. So if you see no grade, don't worry about it. As soon as I input the grades, some score will be there. If you have any questions about that, you can let me know. The Google Doc is a good place to ask those questions today. All right, now getting into today's lesson. If you can print the worksheet, it would be very helpful for you today, but if you can't, you can always do this in your notebook. And for our first problem, because what we're going to do today is we're going to extend on section 4.5. I know you had the assessment yesterday, but there's a few things I left out, a few things that I wanted to reinforce. So I thought we'd do that today. So the first problem is I've given you this graph, and I'd like you to write an equation for it, and then write a second equation for it. Because this equation actually has tons and tons of possibilities. So you can use sine or you can use cosine, and you can try all sorts of transformations. See if you can write at least 2 equations for that. Okay, here's some of the correct answers. The first equation that I noticed for this was negative cosine x. So when I looked at that graph, I said it looks like we took cosine and flipped it over the x-axis. But that might not be what you saw. Maybe you looked at it and said it's cosine moved pi to the right. That's the same graph. Or maybe you looked at it and said it's cosine moved pi to the left. Or maybe you looked and said it's cosine moved 3 pi to the left. So we can take cosine, and if we move it left and right just the right amount, we get the same graph as the negative cosine. So all of these are correct answers. And there are many, many more correct answers that involve cosine. You also can write this as sine. So if you look at this graph and you say, well, it looks like sine. Here's sine. Let me put sine up for you. So there's sine. And if we give it a shove, pi over 2 to the right, it should overlap that other graph. So to move it pi over 2 to the right, I can put in a minus pi over 2 right there. And you can see that this is another equation for that same graph. Or you could take sine and move it 3 pi over 2 to the left, and you get the same graph. Or you could take sine and move it pi over 2 to the left and flip it over the x-axis. You're going to get the same graph. And this one as well. You could take sine, move it pi over 2 to the right, and then reflect over the y-axis, and you get the same graph. These are not the only correct answers. The list of answers goes on and on and on and on forever. So if you have an answer that does not appear here and you want to check it, just go to desmos.com and you can graph one of the correct equations and then graph the one that you have and see if it matches. So that's number 1 from today's worksheet. Here comes number 2. Number 2 is a type of function where we have 2 or more expressions and we are using these expressions on different portions of the domain. Do you remember what kind of function this is called? This is called a piecewise function. So what we want to do to graph this piecewise function is we want to use the sine function anywhere to the right of 0. So to the right of 0 on the x-axis, we want to graph sine. At 0 and to the left of 0, we want to graph this linear function. So you can start with either one. I think I'll start with the sine function since it's the one first up there. And our sine function has usually a y-intercept at 0, 0. And I'm not going to make that a closed circle here. I'm going to make that an open circle because we don't actually want to use sine when x is 0. We only want to use sine when x is greater than 0. And then sine usually goes up to the right, has a max at pi over 2, and then it has an x-intercept at pi. So here's that hill. And then here we have 3 pi over 2, the next quadrant angle, we're going to have a min. And at 2 pi, we'll have a max again. And then to fill the viewing window, I can't quite make it to another max, but I'll just kind of continue on my way. And that's what the graph should look like to the right of the y-intercept. And if you forget what the sine graph looks like, you can always go back to the unit circle. And just use the quadrant angles because all the critical values, all the maxes, mins, and points of inflection happen at quadrant angles. So at 0, sine would be 0. At the angle pi over 2, sine would be 1. So that's why I have pi over 2, 1 on my graph. At the angle pi, sine would be 0, and so on. So if you remember what the graph looks like, you can just graph it yourself, but you can always go back to the unit circle if you forget. Now for the portion of the graph to the left of 0 and at x equals 0, we want this linear function. So this is just a line in y equals mx plus b form. So if it helps you to put the y on it, you can rewrite it. So if it helps to see instead of negative 1/3 x minus 2, if it helps you to see it as y equals negative 1/3 x minus 2, then go ahead and write it that way. So our line is going to have a y-intercept at negative 2. And then the slope is going to be negative 1/3. So for negative 1/3, we can either go down 1 and write 3, which I don't really want to do because I don't want the graph to be over here in this region. But we go like that. Or I can go up 1 and left 3. So if I go up 1 and left 3, and then go up 1 and left 3 again, I can connect the dots and extend. And this side, if you want, you can put an arrow on there because that does continue forever out in that direction with that steepness. But you can't really put an arrow on this side. So if it bothers you to have an arrow on this side and not on this side, then don't put the arrow. You can truncate. You can just chop off the graph at the end. And that's what this graph should look like. Next one is one for you to try. And what I'm going to ask you to do is graph sine of x for x less than or equal to pi over 2 and cosine of x for x greater than pi over 2. So take a moment and try that, please. Okay, and this is what your final graph should look like. So since we're using cosine to the right of pi over 2, at pi over 2, we should have an open circle on the x-axis, go down to a min at pi, an x-intercept at 3 pi over 2, a max at 2 pi, and then just a little more to the right, decreasing there. And again, you can use the unit circle to find these values of cosine, or if you know that cosine starts up here at 0, 1, it's okay to start the graph. See how I just sketched it in pencil? And then just erase the part you don't want. That's how I taught piecewise functions when we did that back in chapter 1 much earlier in the year. So you should have this portion of the graph with an open circle. And then this part was probably a little easier to graph because it went right through the y-intercept. So we're going to use sine when x is less than or equal to pi over 2. So you have your y-intercept at 0, 0 as expected for sine, a max at pi over 2, 1, and then it comes down to the min at negative pi over 2, intercept at negative pi, and so on. And this is a skill you actually need in calculus next year. You will see some examples where we have piecewise functions that deal with graphing sine or cosine. And when we do that, they're usually basic sine or cosine. We don't usually have too many transformations involved. So that's why I kept them basic today. Okay, next example for today. I'd like us to graph y equals cosine pi x. And I'm going to do that with you. So for graphing y equals cosine pi x, you can see that the transformation of cosine here is some sort of stretch or shrink. So to find out what the stretch or shrink is, we're going to do 2 pi over absolute value of b. Our b is pretty much never negative, so sometimes I don't even put the absolute value, as you know. But what we're going to have here is 2 pi over pi, which reduces to 2. So the period does not have to be in terms of pi. We've seen that before, but we've never graphed that by ourselves before. So with a period of 2, first question is that a horizontal stretch or horizontal shrink? That's going to be a horizontal shrink because the period is usually 2 pi, and 2 pi is about 6.28. So our period went from 6.28 all the way down to 2. So that's a smaller period, which makes it a horizontal shrink. And to graph this, what I would recommend is we observe what usually happens with cosine in one full period. Usually with cosine, we start at a max, intercept, min, intercept, max. That's what happens in one full period, and that usually takes 2 pi. But what's going to happen here is we're going to achieve that full period in just a length of 2. So if we realize that our y-intercept is going to stay where it is, it's kind of our anchor point. The y-intercept doesn't change there. Instead of going out to 2 pi for that next maximum, that's going to occur at 2. And then if you look at your maximums, what has to occur halfway in between is you have to have a minimum. So halfway in between would be at 1. So at 1, we're going to have a min at -1. So the point is 1, -1. And halfway between this max and this min has to be an x-intercept. So halfway at 1/2 is going to be an x-intercept. And halfway between 1 and 2, since we have a min and then a max, there has to be an x-intercept. Is that x-intercept a little bit to the left of pi over 2 or a little bit to the right of pi over 2? Teeny tiny bit to the left because 1.5 is smaller than 1.57. So there's one full period of our graph when the period is 2. So to continue that process, every half unit is a critical value, not every half pi, every half unit. So at 2.5, we'll have an x-intercept. At 3, we'll have a min. At 3.5, we'll have another x-intercept. At 4, we'll have another max, and so on. So I know we usually fill the viewing window, but if it's okay with you, I thought we would just stop there. That would be sufficient. I wanted to make sure that I showed you that we can graph when the period becomes a whole number or some decimal. It doesn't always have to be in terms of pi. But it's something that I don't think we need to spend too much more time practicing, because if we ever really needed to graph that, we could go to Desmos and take a peek at that graph. And here it is. So here's the cosine of pi x. That's the one I just graphed. So we have that y-intercept at 0, 1, and our next maximum was at 2, 1, and our next maximum was at 4, 1. And if you look at your graph that you made, you'll see that we have all the same points, all the same critical values that we just graphed. I'm just removing some of them because it got to be so many points right here. So if you compare what I'm looking at in Desmos to the graph on your paper, you'll see you have 0, 1 for a max, 1, -1 for a min, 2, 1 for a max, 3, -1 for a min, 4, 1 for a max, and so on. Okay, next problem. The next one we're going to graph is y equals sine 2x minus pi. Now, you may or may not have noticed that when we were graphing these by hand, we did all sorts of transformations. When you graphed by hand, you did vertical shifts up and down. You did horizontal shifts left and right. You did horizontal stretches and shrinks. You did vertical stretches and shrinks. Sometimes you reflected over the x-axis if this was negative. Sometimes you reflected over the y-axis. Not often, but sometimes we did if this was negative. One thing we never combined in our work yet was graphing by hand with a horizontal stretch or shrink and a horizontal shift. So I want to take a moment and show you how that works because it has slightly different rules than what we're used to. So if you have a horizontal stretch or shrink and a horizontal shift, what you have to do in order to graph this is you actually have to get the x to have a coefficient of 1. So you have to factor whatever number's out front out to the front inside sine still. So I'm going to factor a 2 out of this by dividing by 2. And if I divide this by 2, I get pi over 2. So if you were to multiply this back in, you'd have 2x minus pi. So all I did was factor out a 2 inside the sine function here. So when you combine a horizontal stretch or shrink and a horizontal shift to graph it properly, you actually have to factor that, what I'm calling b, in front of the x and the horizontal shift. So the horizontal shift here is not actually pi to the right. The horizontal shift is pi over 2. And this right here is going to cause a horizontal shrink. So the period, by the way, because it's 2 pi over absolute value b, is going to be 2 pi over 2 or pi, as we would expect. No surprises there. But the surprise is if you combine a horizontal stretch or shrink and a horizontal shift, you actually have to factor before you can determine the amount of the horizontal shift. So just to show you it's correct, let me take you back over to Desmos. Here's sine, and here's sine 2x minus pi. So you can see the period is shortened, and you may not be able to see yet, but the horizontal shift is going to be pi over 2, not pi. So let me go back to the graph paper and walk you through that. So the way that I teach graphing is to do SHRV. It's not the only way to do it, but it works for us. So that's why I stick with it. So we do stretches and shrinks, then the horizontal shifts, then reflections, then vertical shifts. So let's do it that way. So we're supposed to do a horizontal shrink of sine to make the period pi. Okay. So I know you know how to do that. So I'm just going to go ahead and get that graph going. Okay. So there's our horizontal shrink of sine to make a period of pi. Now what we're going to do is shift it pi over 2 to the right. So pi over 2 to the right means that we're going to go 1 tick mark to the right for all of those critical values. So the intercept that's usually here goes pi over 2 to the right. The max is going to go pi over 2 to the right. The intercept goes pi over 2 to the right. The min goes pi over 2 to the right. And you can start to see the pattern that I have going here. So every half tick mark, I have a critical value. So if I move this guy over, pi over 2 to the right, move this guy over, pi over 2 to the right, we can fill in the rest of the curve using that pattern. I am going to fill the viewing window for this one because it's not too much. The previous one would have been a lot of hills and valleys to draw. Okay, and there's our final graph. So if you notice from the original y-intercept, see the y-intercept here is 0, 0. We did not move that pi to the right. We shifted that pi over 2 to the right is what our shift was. So like I said, this is one way to go about graphing. If anyone has been wondering about order of operations, you actually can first shift pi over 2 to the right if you want and then shrink it. But you would use a different, what I call an anchor point. I like to use the y-intercept as the point where I start and do my stretching and shrinking from. If you wanted to follow stricter order of operations, you could do your horizontal shift pi over 2 to the right, and then your anchor point would be that 2. Let me see if I can show that on Desmos. And this is tough stuff to show. This is why I saved this for the day after the assessment. Even if we were in class together, the activities we're doing today would have been done the day after the assessment. Because it's important to me that I show them to you, but not important enough for us to spend a lot of time practicing. Because if we ever needed to graph this, we could graph it on Desmos or on a graphing calculator, which is what I'm going to show you next. Okay, so over to Desmos. And so, like I said, let me first show you this graph is the same as when we factor out the pi over 2. Okay, so they are indeed the same graph. And then what I like to do is I like us to do the horizontal shrink first. So let me show just the sine graph with the horizontal shrink. And then we give this a shove pi over 2 to the right. And we get that graph. Another way to do it is to actually take sine and move it pi over 2 to the right first. So here's sine. You could move it pi over 2 to the right first. And then when you go to do the horizontal shrink, you're going to end up with this graph, but the y-intercept is not what remains the same. It's not the anchor point. Okay, and when I taught you horizontal stretches and shrinks, we always started at the y-intercept. So if you want to do the horizontal shift first, sorry about that. If you want to do the horizontal shift first, your anchor point is not the y-intercept. Your anchor point is what used to be the y-intercept. So that point there used to be the y-intercept. That's where you're going to stretch or shrink from. So you're going to bring this max in to the left. You're going to bring this intercept into the left. You're going to bring this min into the right to get that graph. So this is the point where you're starting your graph from. So I personally would stick with SHRB because it works. It technically doesn't follow all the order of operations, but it gets you correct graphs. So that's why I like to teach that, because I think it's good for what we're doing. If we wanted to graph anything really complicated, we put it on Desmos or the calculator instead. So this was an example for how to do a combination of a horizontal shift and a horizontal stretch or shrink. And we probably won't graph any more of those by hand this year. Okay, but like I said, I did want to show it to you. The last part of today's lesson is to show you how to graph on a graphing calculator. So if, the past two examples that we just did, if you're thinking, oh, those were a bit much, because I bet 1, 2, and 3 were probably fine. Probably liked those. 4 and 5 were probably like a little weird. Don't be upset or concerned about it. 4 and 5 are just examples I have to show you. It's not something we're going to spend a lot of time practicing. Okay? But the next thing we do, you definitely want to learn, is how to graph on the calculator. So let's do that now. To graph on the calculator, you can go into y equals and hit sine x. And when you hit graph, if you're in Zoom Standard, you might see what I see, or you might not. It depends on what mode you're in. So if you're in radian mode, when you hit Zoom Standard, you get this graph. If you're in degree mode, when you hit the Zoom sine of x and you hit Zoom Standard, you get this graph instead, which you pretty much can't see any of it. It's there. If you hit trace, you can see that the graph, it is there. It's just super close to the x-axis. So first thing to acknowledge, when we graph trig function in this class, we only graph in radians. It is possible to graph in degrees, but we only graph in radians. Okay? So you should write that down. We want to be in radian mode when we graph. And this window, as you can see, may not really be that appropriate because it goes all the way up to 10, which seems excessive, and it goes all the way down to -10, which seems excessive. If you think about our graph paper typically only goes from -4 up to 4 on the y-axis. Because even if we want to take sine and move it up or down, we could probably fit it. The other thing that probably doesn't make too much sense here is on the x-axis, we're counting by ones. 1, 2, 3, 4, 5, 6, and so on. What might make more sense is to count by pi over 2s, because that's what we typically count by on the x-axis. So the good news is the calculator has a good window built in for us. So we don't have to go into the window and change everything manually. What we can do is hit Zoom Trig. And if we go to Zoom Trig, you're going to get either this graph, or if you have the newer color graphing calculator, you get this graph. Either one is just fine. So what Zoom Trig does is it sets up your window to go from negative. So we're going to investigate the older calculator first. If you have the newer one, we'll investigate that in a moment. So for the older calculators, it goes from about almost -2 pi. Negative 2 pi would be about negative 6.28. I don't know why they make it fall a little short of that. It would make more sense to me if they just went to 2 pi. But it's almost negative 2 pi to 2 pi. And look what the scale is on the x-axis. It's 1.57. So what we have here is every tick mark is pi over 2. So that's pi over 2, pi, 3 pi over 2, just like we're used to. And it goes pretty much to 2 pi. For the y min and y max, it goes from negative 4 to 4, just like the graph paper we've been using. So that's a nice viewing window. So you want to write down zoom trig, and it's zoom 7. So you can either scroll down to 7, or a quick way to get zoom trig, guys, is you can hit zoom and hit the number 7. You don't even have to hit the up down buttons. You can just hit the number 7 and it'll switch to that for you. Now, if you have the newer color graphing calculator, when you are in radian mode and you hit zoom trig, these are set to show you a little more than the older graphing calculators. And neither one's better than the other. This is one more what you're used to because we're used to seeing 2 full periods. But what this does is it sets you up to go a little bit past 3 pi and a little bit past negative 3 pi. Because if you look at the windows, see the y min and y max are the same. The x scale is still 1.57, 2 pi. This is pretty close to negative 3 pi and positive 3 pi, because 3 pi would be right there where that maximum is. So it just goes a little bit further to the right after that. So zoom trig, either one is just fine. If anyone with the newer graphing calculator prefers the old window, you can just go to your window and change it. You can make it negative 2 pi. Once I move my cursor from here, it's going to convert that to a decimal. That's fine. And 2 pi. So there's nothing wrong with the window on the new graphing calculator. It's just different than the one that's on the old one. But if you prefer this, because this is what our graph paper looks like, just set that window yourself. So let me show you that window one more time. From negative 2 pi to positive 2 pi was the only change we made. Okay, almost done with the graphing calculator part of today's lesson. The next thing I want to show you applies especially to those of you who take physics. Because when you go to physics class, you probably switch over to degrees and radians and use both sometimes. So I just want to show you what happens if you are graphing and you are in degrees. So take a look at what's happened here. So the graph is only showing this little teeny tiny bit. Here's the reason. If you look at your mode is degrees. If you look at your window is set to radians. There's a disagreement here. So I'm going to show you something. I'm going to hit zoom, trig. And there's our sine graph. Looks pretty good. But what's kind of interesting about it is if I hit my window right now, it's in degrees. It goes from almost negative 360 to almost 360, and it counts by 90s. So we can technically graph in degrees. This is 90, that's 180, that's 270, and almost 360. So you can graph in degrees, but we don't typically do that. We graph in radians. So let me put it back to radians, and let me hit graph. Ready? That doesn't look right, does it? Okay, because what's happening here is we have a disagreement of the mode in the window again, because my mode is set to radians, but my window is still set to degrees. So again, anybody in physics, this won't happen to you a lot, but you just want to be aware of it. So what you can do is if you set your mode to radians first and then hit zoom trig, you're never going to have an issue. But if you forget and you had been in degrees, just make sure you get over to radians and hit zoom trig. And sometimes if you just hit zoom trig a second time, it'll work out for yourself. Because whatever mode you're in when you hit zoom trig, that's what your window will be set to. So sometimes just hitting zoom trig a second time, if you've adjusted over to radians, will do the trick. So as far as notes for the graphing calculator portion, at minimum, please write down that you need to be in radian mode and zoom trig. If you want to, you can write down you might have to hit zoom trig a second time if you weren't in radians before. Or you can write down, make sure you're in radians before you hit zoom trig, just to avoid that mismatch with the window and the mode. If you have the newer graphing calculator, it goes from about negative 2 pi to 2 pi on the x-axis, negative 4 to 4 on the y-axis. Feel free to sketch that if you want. The newer graphing calculators have an extended x-axis from just past negative 3 pi to past 3 pi. And if you want to write that down, feel free. But at minimum, please write these down. And this is just the first time we're graphing in the calculator. It's just a little introduction, because what we can do after this is we can move sine graph up one. We can graph sine of x moved pi to the right. You can graph them on the same plane if you want, or you can graph them separately from each other. We can graph cosine. We can move cosine up, down, left, right. We can stretch it, shrink it. Let me go back in. I'm going to get rid of these. Okay. Let's graph 4 cosine. Do a vertical stretch of cosine. So you can still graph all your transformations on here. And we'll be using this sometimes in the next few weeks. Thank you guys for watching today. And I just want to reiterate, just want to say it one more time. For today's lesson, you were probably fine with 1, 2, and 3. That's great, because those are skills that you need to have that'll come back. If you were uncomfortable with number 4 and 5 today, do not panic, do not worry. Those are just little extra things that I need to show you just to make sure I've shown you the technical, correct, and all the things we can do. But as far as the practical work that you need to be prepared for the rest of this year and AP Calculus, you don't need to stress on 4 and 5. Okay, you've seen it, but we're good now. All right, thank you guys, and I'll see you at the next lesson. Bye-bye.